All right, so here we go. We're continuing on with chapter 15. And we're going to continue to talk about the central limit theorem. Okay? Now remind me, what is a good definition of that? Bias probability? No, that's not the right definition.
As the sample size increases, the mean becomes approximately normal.
As the sample size increases, that's pretty close. As sample size increases, the sample mean becomes approximately normal. There's a big if.
If it's a normal distribution.
Well, now, even if it's not a normal distribution. That's what's cool about it. So what I'd like to do, we're running off the board here. What I'd like to do is give you a for example, okay? So, let's see here. Oh, by the way, since I was just looking at my calendar there,
Are we gonna have class on Wednesday?
are we gonna have class on Wednesday?
Next
Yeah,
one. Yeah.
you're gonna be out of town?
Yeah.
We might have a test that day.
Oh, so it's my grade.
Yeah, it does suck pretty good. Let's see here. It's not the greatest angle, I apologize, but, speaking of the test, so my question is, we'll either have it on Monday or Wednesday, kind of depends. I was thinking chapter 16, might take 2 days, but it might not. My question is, would you rather have the test in this classroom or in our regular classroom where you don't have computers in the way?
Regular classroom.
Regular classroom? Okay, we'll probably do that. Towards the end of the week, I'll let you know if it's either gonna be on Monday or Wednesday. The computer test will be Monday, Tuesday, or Wednesday in the testing center. But the written will be either on Monday or Wednesday. It'll kind of depend on how we do this week. But I think I'm probably leaning a little closer to Monday. So you might be lucky if you take your test Monday.
I leave Friday.
Oh, that's a problem.
Yeah, so can I take it Friday? Okay.
Okay, talk to me after. All right, so, here, let me do, this is an example that I want to do. Let's say, that, we have a school of 900 students that are normally distributed with a mean of 100 and standard deviation of 15. I want to use a uniform distribution to simulate these 900 students. Okay? All right, so here's what I want to do. Okay? I'm going to use a bunch of random numbers, ran between. And I'm going to pick the number 75 and 125. Okay? If you guys want to follow along, this will be a fun one. Okay? Now, I'm going to copy this over 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. You know what I'm going to do? This will be much easier if I put this on the top row. I'll put that back later. Okay. I'm gonna copy this down 100 rows. Okay? Now, do you guys remember how to get these to quit changing? Because right now they change, right? How do you fix that?
Right click.
Highlight your data. Right click.
Copy and repaste it.
We're gonna copy, by the way, I need to make sure my totally on there, okay? Right click, copy, and right click, paste, click on the 1, 2, 3. Now when I type, these don't change anymore, okay? Now here's what I'm gonna do. I'm gonna insert a couple rows here. I'll put this back so that we can see what we were talking about. Okay, so pretend this is a school of 900 students. Okay? Now, if these are random numbers, do you think that they will look normally distributed? Who says yes? One who says no. Only one person voted. Okay? Because I've got 900 here, I'm actually going to use the histogram maker because it's big enough, probably. Let's see. If I say insert recommended charts, histogram maker, does that look normal to you? Sure does not. I would have expected it. Okay? If these are random numbers, what should it have looked like? What? It should not have looked like a bell curve. Should not have looked skewed. This is interesting because I don't know why, because these random numbers between 75 and 125. Notice it's going from 76 to 131. I have a feeling if I had done this manually myself, it would have worked better. This histogram maker in Excel isn't the greatest. But normally, here, let me show you that here, I would expect random numbers to look like a box. Okay? And if I started at 75 and 125, I would expect a rectangle. Okay? Now, and I have a feeling if I'd have done this manually, it would have looked better. Okay? They picked some weird numbers there. Now, my question is, if this is what we would call a uniform distribution, which means that these are equally all values equally distributed. Okay? Now, if you were to guess, looking at this picture, what the mean would be, what do you think the mean should be? Cassidy, what do you think?
I'm still putting everything in, so I'm not sure yet. But the mean right there,
Yeah, this picture here.
100,
100, how'd you come up with that?
and it's right between some.
Right smack dab in the middle, okay? You would expect the mean to be 100, and that is correct, okay? Now, what is the distance between 75 and 125? That's 50, okay? Now, one of the nice things about this is, do you know the area for a rectangle? It's length times width, right? If this is a probability distribution function, what should the sum of all of the probabilities of x equal? The latter? What? Yes, but what should all the sum of the probabilities be? One or 100%, right? Okay? So if my length times width has to equal 1, and my length is 50, and my width is that, and it has to equal 1, what would be the width be? Right, rectangle. And by 50, So your width equals 1 over 50. So the nice thing about this is, because the sum of these has to equal 1, in order to be a probability distribution, the sum always has to equal 1. Whatever your length is, your width is going to be 1 over that. Does that make sense? Okay? So this is what we would call a uniform distribution. Okay? Does not look normal. My graph even looks worse, but okay? So here's what the central limit theorem, sometimes abbreviated as CLT, says. Regardless of the underlying distribution, which is clearly not normal, okay, the sample mean becomes approximately normal, even if the underlying normal, even if it is not normal, if the sample size is large enough. Okay? So then the next question is what? Dylan?
You're asking what the next question is
What would
for?
be the next question?
How large the sample size?
How large should it be, right? How large? Okay? And it depends on your type of data. If you're dealing with proportions, then NPQ has to be greater than or equal to 10. If you're dealing with means, N should be greater than or equal to 30. Okay? So there's actually 2 rules to that. Okay? If you're dealing with proportions, such as on your final project, remember? By the way, who started collecting data? Don't collect it all last week. Okay, you can collect data now. I did make that announcement last time in class, didn't I? We got it. Okay? This is the rule, okay? Because you're looking for the percent of people who want to see Trump face a primary opponent, right? And so you're going to use this rule. If you're doing something like potatoes or cars, your sample size should be at least 30. Okay? Now, I did let you get away with only 30 on the phone, but actually that's not big enough. Okay? But I also know the phone data is really hard to collect. And so you might have to call 300 people to get 30 people to answer. Okay, so don't make Abby call everybody, all 300 people, because it's rude to her. Okay, you should all have an opportunity to have people get mad and hang up the phone. Okay, don't make Abby do everything. Okay, so split that up between everybody and make sure that you get at least 30 responses. Okay, all right. So here's what we're saying. Okay. As the sample size becomes bigger, you're actually going to do so if I did a sample, what I'm saying is my X bar is going to equal 100 in this case, according to the central limit theorem. Let's see if that is true or not. Okay? All right, so let's go back to our thing here. Okay? So, one of the nice things about this data here, technically I should have an N of 30, right? But sometimes you can get away with smaller values, okay? So I'm going to figure out the sample mean, okay? And I'm going to do it on each row, and I've only got 9 in here, okay? Sometimes the central limit theorem works even when N is less than 30, but you should really always ensure that N is greater than 30, okay? How would I find the sample mean, N, on this first row?
You press equal average.
Equal
And
average.
you add all.
And we're going to just highlight this one row, okay? So what we're saying is I've got a sample, I've got a population of 900. I'm doing a sample of 9, which is actually much smaller than 30, right? Sometimes it'll work anyway, and I have a feeling it's going to work. So I got a sample mean of 104, okay? It says here that my mean is supposed to be 100 and my standard deviation is supposed to be 15. So what I'm going to do is I'm going to copy this down for every row. Okay, this is the central limit theorem in action. Okay, so I've just created 100 samples of size 9. Okay, now the first time I got 104, then I got a 95, and a 98, and a 98, and a 100, and a 106, and a 101. You can see that these vary quite a bit. Do you see that? Okay. All right. So normally, when you guys are doing a sample, you're not going to do 100 samples. You're only going to do 1. Okay. I've just done 100 samples of size 9 in this case. Now, my question here is, what if I did a mean of the means? And also, what if I did mean of the population? Okay? Because this is a school of 900, I can actually find the population mean. Normally, you're not going to be able to do that, right? Okay? How do I find the mean of the population? Allie?
What? I'm sorry, could you ask that one time? I'm trying to show her what it is.
Oh, I was going to ask Allie how to find the mean of the population.
You do equals average,
Average.
and then you highlight all of the.
Highlight all of my data. All 900 students in this case. Okay, so with my simulation, it was supposed to be 100. Let's see how close to 100 I get. Drum roll, please. 100.01, that's pretty doggone close, right? That's pretty good simulation. Now, my question to you all is, if I did a mean of all my means, I'm going to do a mean of all of these here, okay, before I press enter. Don't you press enter yet, but who thinks that if I do a mean of my mean, it will be exactly the same as the mean of the population? One person who thinks it will be different, slightly. 2 people, 3, say it's going to be different. Okay, here's your drum roll. How about that? It's exactly the same. Okay? And here's what else I'm going to do. I'm going to create a histogram of these 100 means. Okay, now, that doesn't look very boxy, but pretend that's a box. Okay? I'm going to insert, I'm going to use my histogram anchor right here. What do you think of that? How would you describe the shape of this graph, this histogram?
A normal distribution.
A normal distribution, wouldn't it? So even though the underlying distribution is clearly not normal, I'd probably call this one bimodal and left skewed, right? Okay. The distribution of the sample means is normal, which is kind of what I drew on the board here. Okay. The underlying distribution is a uniform distribution, clearly not normal, but the distribution of the sample means is normally distributed. Okay? What I've just demonstrated to you using real fake data is the central limit theorem. Okay? Now, the 2 important rules that people always forget, they remember that n is greater than 30, but they always forget about the proportions. So this central limit theorem works with both proportional data and means, okay? So when you're doing your project, this is the rule you should use for your poll. This is the rule you should use for your potatoes or your speed limit, a minimum of 30. And you should also verify, because this isn't a magic wand where I say, oh, it's automatically 30, therefore it has to be normally distributed. No, you still need to check your data, but it does work every time. Okay? And so check and make sure that your distribution is normally distributed. Does that make sense? Okay? All right, so that is the central limit theorem. So let's do some examples here. I'll do this on the board. Okay? All right. The mean weight gain during pregnancy is 30 pounds with standard deviation of 12.9 pounds. It is known the population is skewed right. An obstetrician in a low income neighborhood obtains a simple random sample of 35 patients and finds the mean weight gain is 36.2 pounds. Should she be concerned her patients gain too much weight? Okay. All right. So let's go through this here. Wow, that's really out of focus. Focus. Focus, I say. Come on. Was anybody going to read that? There we go. Okay. So mean weight gain is 30 pounds, standard deviation of 12.9. It is known the population is skewed right. How should I draw that for you? How would I draw a skewed right distribution?
We could just use a bell curve and have it skewed to the right.
Well, it's not a bell curve if it's skewed to the right.
Okay.
Okay? So a skewed right would look something like that, correct? So is it normal? Not normal, okay? The mean on here, what letter do I use for the population mean?
You,
Use mu equals what?
30.
30 pounds. Okay? All right, so, and I've got a standard, so in this case, in fact, you may want to write these down. Mu equals 30, and it says the standard deviation is 12.9 pounds. Which standard deviation is this?
Just population.
Population, so I use what letter?
S. No, standard. Just S.
It's not S. S is for,
Is it D?
no, it's going to be sigma, the Greek letter sigma. Okay? So I've got mean weight gain is 30 pounds, standard deviation is 12.9, and it's skewed right. So it looks something like this. Okay? All right. So obstetrician from a low income neighborhood, can I figure out this color? Okay? Obstetrician in a low income neighborhood contains a simple random sample of 35 patients. What's 35?
Simple.
What letter do I use for that?
S.
What'd you say?
S,
S for sample? No, S is not for sample.
X bar.
X bar is not for sample. If you learn this little thing, this is going to help you solve your problems.
Isn't it N?
N for sample size. Here, okay? 35 patients, finds the mean weight gain is 36.2 pounds. What is 36.2 pounds? X bar, because it's the sample mean. And that's all we have, right? Okay? So in this case, what we're saying is, according to the central limit theorem here, okay, these patients have gained more weight, 36.2 pounds, right? According to the central limit theorem, what should my X bar be distributed as? What should it look like?
Along the box.
A box?
The normally distributed limit would be above.
Would be a bell curve, right? Okay, so even though the underlying distribution is not a bell curve, X bar is normally distributed because of the central limit, right? Is my sample size large enough? Yes, because 35 is greater than 30, right? N is greater than 30, and I'm dealing with means. Okay? All right, so now, remember a few weeks ago, I told you guys that I was going to give you 2 formulas for the z-score formula, and I told you that they were really the same, and then I told you which one to use, because it always works. What was that formula?
Beta,
Z equals,
beta over square root of N. I don't know, the circle with the tail.
okay, what's the numerator first? You're right for the denominator. What'd you say?
I said X minus X bar.
X bar minus
M, or mu.
mu over
Beta.
sigma over the square root of
N.
n. Okay?
So it's the sample mean minus the population mean divided by.
The population standard deviation divided by the square root of n. Okay? And remember, I said up when we did this before, I said your n was always 1,
No, it's not.
except for not anymore. Now I have my own n here. In this case, it's going to be 35. Okay? All right. So in this case, z equals what? Let's see if I picked on Annie. I don't think I've picked on you yet. X bar is, in this case, 36.2 minus 30 divided by
12.9.
12.9 over the square root of 12.9. Right? Okay, so if you identify these all as you're going through this problem, it's going to make plugging it in here really easy.
You still had N is 35.
Oh, you're right. It was 35. I did the standard deviation again. 35. That's correct. Okay? All right, so let me punch this through my computer here really quickly. Okay, so z equals, the numerator is 36.2 minus 30 equals 12.9 divided by the square root of 35. So this is that divided by that. Okay, and I've got 2.84. What does that mean?
Isn't that our z-score?
So what I've done is I've converted this now. I'll draw this again. I've converted this over here to a standard normal distribution, which has a mean of. What's the mean of the standard normal? Nope, not anymore. Standard normal.
32,
Standard normal always has a mean of
1,
0.
0. Always has a standard deviation of
1,
1. And I got 2.84. I'm 2.84 standard deviations away. Okay? Now, we're concerned that the patients are gaining too much weight. So on this graph here, is it the left side or the right side that would tell me if they were gaining too much weight?
Oh, right.
It would be the right side. So I want this area here. Okay? That's known as my p-value. How do I find that value?
First, you have to find the value to the left.
Okay, how do I find the value to the left?
Look on your
Got two methods, right? I can use the chart, or I can use the computer. Which one would you like to do first? You need to know both methods for the test.
the chart.
Chart method first, okay? So, if I'm using the chart, I'm going to use this one here. Oh, this is, I hate it when autosave is on, that drives me crazy. Okay, so I got 2.84, 2.801, 2, 3, 4. I got that value. Is that the correct answer?
No,
No, because
that's the value to the left.
that's the value for the left. So in order to find this chart, I'm going to do 1 minus 0.9977, which equals 1 minus that number there, 0.0023. Okay? Now, we should be concerned, or maybe I should say it this way. It is statistically significant if your p-value is less than 0.05. Okay? Is my p-value less than 0.05? Yes. Okay? So what we're so should she be concerned that her patients are gaining too much weight? Yes. Okay? This would happen 0.2% of the time if it was just random chance. Okay?
Is there a reason why you put less than 0.05, or where'd you get the 0.05?
Yeah, so basically, well, think of it this way. If you were right 95% of the time and you were wrong 5% of the time, would you be happy with that test? Is that great on your test? Okay, so what we're saying here is this is the probability that you're wrong. If you're wrong less than 5% of the time, we're going to say that it's statistically significant. Now you can choose whatever value you want. Typically we refer to your alpha as 0.05. Basically, this is the probability that you say I might be wrong 5% of the time. But if you're right 95% of the time, you're going to be happy with that, right? You can choose whatever alpha you want. The most commons are 0.10 or 0.01. Okay? But if I don't tell you what your alpha is, assume that it's 0.05. If it happens less than 5% of the time, you're going to say, yes, that's statistically significant. Okay? All right, now to use the computer, you're going to do the same thing. What? I know, I'm trying to finish this. 1 minus norm S dist of 2.84, and that gives you the exact same value there. Okay? All right, so your homework on chapter 15 is due on Wednesday. I was hoping to do one more, but we only got through one problem here. Okay? So, see you all on Wednesday. Thank you for letting me use the markers.
Can I just email you? Cause I have to go to a different building.
Good job with that.